Okay, so differential equations are basically equations in which you have the rate of change in a variable, and see, an equation relating two variables with at least one term containing the differential coefficient is called a differential equation. Like this is a differential equation because it has the differential of y with respect to x in it. Then this is a differential equation where there is a second order derivative involved, there is a first order derivative involved. These are all differential equations. If you have a look over here, these are all differential equations. All of them have a differential involved. Even when you say as simple as dy by dx is equal to 2x, this is also a differential equation. Doesn't mean that in a differential equation everything has to be mixed up on one side. I mean, even this is a differential equation. And by the way, you have at a very rudimentary and a very fundamental level, you guys have solved differential equations in integration. How do we go back to the original function from here? Let's suppose there was some y is equal to something, and I differentiated and I came to this. How do I go back to the original function? You've done this in P1 integration by integrating on both sides, right? So you integrate on both sides with respect to x, and then you go back to the original function. So this becomes y, because y's derivative with respect to x is dy by dx, so dy by dx integral with respect to x should go back to y. And this becomes 2x squared by 2 plus c. So basically it's y equals x squared plus c. Then you have those values that you plug in to get the constant integration out, and then you have the original equation. Right? If you remember, we've done this simply. This is a very simple way of solving a differential equation. What you have done by integrating on both sides to go back to the original function is you've solved a differential equation. Now we didn't say it in these terms, oh, you're solving a differential equation last year, because it wasn't required. Now we need to recognize it in the way that, okay, so basically by integrating on both sides, what I have done is I've solved the differential equation. And solving a differential equation actually means from the differential equation going back to the original equation. That's when you say I've solved the differential equation. I've gone back to the original equation without the differential. So I've gone back to the original equation. Now if I say when x is 1, y is equal to 4. Let's say. Then you plug these values in, you'll say, okay, fine, so 4 is equal to 1 square is 1c, so c is equal to, which means the answer is x squared minus x squared plus 1. Now you've done this at a very simple level, and even integration 1 in P1 you've done this. But we didn't recognize it with the perspective of solving a differential equation. So basically you've solved a differential equation. Now what you need to recognize is this. So this was a differential equation that we started off with. We integrated both sides, came down to this, and then I needed some particular values that I plugged in to get the constant integration out, and then I have my complete solution. So this is your complete solution basically. Now in the study of differential equations, this particular form, this thing that you get after doing the process and you obtain this is called a general solution. Now, why is it called a general solution? Is because I still don't have the complete answer, because I don't know C. I still don't know C. Right? So till the constant integration survives, I call it general solution. Till I don't have all the constant values with me, I call it a general solution. It's called a general solution because it could be generally anything depending on what the value of C is. Once I plug in certain values and get the value of C out and rewrite the complete equation, this is what we then call a particular solution. So and these values that you used to get the constant integration out, these values are called boundary values. So you plug in these boundary values and you get the constant integration out, and then the complete solution that you write is called the particular solution. Why is it called a particular solution? Why is the word particular being used? Is because for these particular values, for that particular incident or for that scenario, this is the equation that relates the scenario. So that's what's called a particular solution. Are we good? Very basic we have done. So it's not something alien to us, we've done this before. It's just that different differential equations require different processes of getting back to the original function. So there are many kinds of differential equations. Now first we'll understand what kinds of differential equations we have, and then we'll come down to which kind requires what kind of process to solve it. Solving a differential equation again means what? Coming back to the original equation. That's what solving means. Right? So first we need to understand what different kinds of differential equations we have. So in a very basic way, although I'm not getting into too much detail because there are many kinds of differential equations. So I'm just broadly explaining you the kinds. So differential equations are looked at as, I haven't mentioned this way, but they're looked at as either partial differential equations or ordinary differential equations. These differential equations that you see with dy by dx and d square y over dx square and all these over here, these are all ordinary differential equations. They're called ODEs, ordinary differential. So why they're called ordinary differential? Because the differentials that are all involved over here is the simple dy by dx or the simple second derivative. This is an ordinary differential. There is another kind of differential which you haven't studied, which you will study at university. It's called partial differentiation, which we haven't studied. So any differential equation that has partial derivatives inside it is called a partial differential equation. So we will not come across those because we don't do partial differentiation. Therefore, we're not going to be coming across any partial differential equation. So because we do the ordinary differentiation, so the differential equation that we will come across is going to be ordinary differential equation. Okay, so these are all ordinary differential equations. Now within ordinary differential equations, then how do we classify different differential equations? We classify them according to their order. The order of a differential equation is determined by the order of the differential in your differential equation, the highest order inside. Now, if you look at this differential, this example, there's only one dy by dx in it. And this is a first order differential. This is a first derivative. The first derivative, it's just a first derivative, right? So therefore, it's a first order differential, and therefore this equation is a first order differential equation. Whereas if you look at this one, there is a first derivative and there is a second derivative. So the highest one in the equation is the second derivative, which means the second order differential is the highest differential in the equation. Therefore, this equation is a second order differential equation. So there can be a third order differential equation, just means d cube y or dx cube over. There could be a fourth order, there could be a fifth order differential equation. So then after you come down to whether these are partial differentials or ordinary differentials, then you have to see, is it a first order differential equation, is it a second order differential equation, what kind of an order differential equation it is. Okay. And then there are other classifications which I'm not getting into, but broadly this is something you must know. Okay, so we can distinguish between a first order and a second order now, right? You have no problem with that? Okay. So do you think all of them are first order differential equations?
Yes.
Yes, because all of them have the first derivative in it, right? If some of them had a second derivative also in it, it would have been a second order differential equation. If some of them had a third order derivative in it, like a d cube y over dx cube, it would have been a third order differential equation. Are we good till here? Okay. In your course, we will only be doing first order differential equations. We don't do second order. Further math has second order differential equations in it. We are only doing first order differential equations. Now, let me tell you, in first order differential equations, there are many kinds of first order differential. There are I think 4 to 5 kinds, if I am not getting 4 to 5 kinds of first order differential equations. We are going to do only one of them. And we are going to do the simplest one, which is the separable variable equation. So, if you see over here, we are going to only do solving a separable variable equation. So, we are not touching upon the Bernoulli's equation or the exact equation. We are not doing all those. We are only doing the homogeneous separable. We are not doing all that. We are only doing the separable variable equation, which is the simplest one. That's in the course. Okay, so I think this we just discussed. if you have a look, this we've already discussed. Order of a differential equation is determined by the highest order differential coefficient of the equation that we just discussed. Solution of differential equation is the equation relating the two variables directly without the differential coefficient. So when you come back to the original equation, initial solution contains the constant of integration and is therefore called a general solution. We just discussed that. And a particular solution is obtained by replacing the constant with the value found using the initial condition or the boundary condition. I'll tell you what's the difference between initial condition and boundary condition. I'll just tell you in a moment. Okay, so we are going to be solving separable variable differential equations. Okay. Now, why is it called a separable variable differential equation? Because this is a kind of differential equation, and this is the first order differential equation where you will be able to separate the two variables on either sides of the equal to sign. That means if it's a y and x differential equation having y and x as the variables, then you will be able to have all y's on one side of the equal to sign and all x's on the other side of the equal to sign. You will be able. If you're able to have this, then you have a separable variable differential equation. If you're unable to do that, then it means your differential equation is not a separable variable, but it's a different kind of a differential equation which needs a different kind of procedure for the solution. Now, this is why I'm explaining in a very general way. dy by dx is equal to, let's say it's a mixture of x and y's. It's a mixture of functions of x and y's. And somehow it is as such that I can separate it. So if I come across like this, if I am able to separate them and form something like this where I have all x's on one side and all y's on one side, that means I have got a separable variable differential equation. Now, where do you get the y's and where do you get the x's? That's the question. अच्छा यहाँ उल्टा लिख दिया गया. Please just make a note of this. This should be h of y and this should be g of x. Just please make a note of this. There's a error in that. This should be h of y and this should be g of x. Let me just correct it. It should be like this. H of y equals g of x. So what I'm saying is you've gotten all the y's on one side and all the x's on the other side. Now, your question should be, which side should we keep the y's and which side should we keep it? This is very important. Now, see, the differential that you have is d by dx. If I want to split this differential, this is how I would end up splitting it. The dy would remain there and the dx would go to the other side, right? Which means all your y's should be on the left and all your x's should be on the right. All your x's should be with dx, all your y's should be with dy. Right? So if it's a dy over dx, then obviously your dy will remain there and your dx will go on the other side. So you have all the x's on the right side with the dx and all the y's on the left side with the dy. Are we good? I can show you the other way as well. If it was something like this, let's say f of x dx by dy, and this is let's say g of y. I'm just making it for you. Now this is dx by dy. So if I were to split this, I would have the dx on the left and I would end up having dy on the right, because this would go on the right side, the dy at the bottom of it. So which means then on the left side I must have all the x's and on the right side I must have all the y's, because my dy is on the right. So it depends when you split, it depends where your dx is and where your dy is, and accordingly you will have to have your functions with them. Does it make sense? Are we good? Okay. So this is how we will be separating them. Alright, once we have separated them on either sides, like you end up having h of y dy and you end up having, let's say, g of x dx. Once you separate them, then what you do is you integrate on both sides. So the left side will be integrated with respect to y and the right side will be integrated with respect to x. Okay. This is how it goes.
After this, we will write the general solution.
Once you integrate, you will come up with a general solution. You will have the quantum integration with you, and once you plug in the values are given to you, you plug in the values, get the values, see out, rewrite the equation for a particular solution. Right? If the values are given. If the values are not given, then obviously you will have to state it with your general solution. That would be your answer.
हम लोग C दोनों sides में.
अच्छा, C आपका दोनों साइड में आता है. Good question. Your C does come on both sides. I'll be saying. Let's say इसके answer के बाद you're getting a C1, you can call it, and after this answer you get a C. But at the end, but we don't write the c on both sides. The reason is because even if I do write it, I can take I can take one c on the other end and combine it with the other c. Now whether it cancels out or it combines into another constant, the point is it will combine to form another constant. So there's no point in writing two constants on either side. So you just write one constant on one side. It's up to you whether you write that one constant on the left or you write one constant on the right. That's totally okay. It doesn't make a difference. But there's only one c that you will write either on the left or on the right. Because ultimately they will merge into one constant. So there's no point in writing two constants on either sides.
You have to add the wrong order.
No. At the end you will get even if you get two separate c's, they will combine to form one c and ultimately you will end up with one c. So rather just have one c and then find that c which the values of 0 to 0 rather than finding two c's. Okay. So if the first order differential can be expressed in this form, and then it is called a separate variable equation, take all y's terms on one side of the equation along with dy by dx and all x terms on the other side. So the y terms actually go with dy by dx because the dx doesn't get split to the right side. Even if you don't think of it that way, you can even think of it this way. See, it's just a perspective. Let's say I don't split the dy by dx, I just separate the variables. Now basically this is what I have. Now either you can think of from this point on, you can think of splitting the dx and the dy and then integrating, or you can think of it in this terms that I'm going to differentiate with respect to x on both sides. So automatically ये तो चलो ठीक है, this is fine. G of x, function of x, we will integrate with respect to x. This is function of y with dy by dx, and when you integrate with respect to x, this automatically becomes. So either way, it's the same thing, and you will end up with the same. You will end up with the same thing. It's just a way of looking at it. Are you good? Actually speaking, this is what is happening. The splitting of the dx is just a shorthand way of representing the thing. Just like x, 2x equal to 1, so we say x equal to half. It's just that way, but nobody says x equal to half is wrong because we didn't show in the middle that we are dividing by 2 on both sides. But we all know that we are dividing by 2 on both sides. It's just like that. So we all know basically with respect to x on both sides, we are integrating, and that's how you end up with the dy on the left and you end up with the dx on the right. So ultimately it comes out the same. Okay, great. So maybe we can have a look at this very simple one to start with. Find the general and the particular solution of the equation. Okay, see x, y function. Now I can easily, now I know dy by dx, so I need to keep all the y's on the left, and because the dx will go to the right, so I'm going to keep all the x's on the right. So this comes down to be this, and this comes down to be x. Agreed? I can say, okay, now I integrate on both sides. So I end up with the integration of with respect to y on the left, integration with respect to x on the right. So what I'm ending up with is e to the power 2y dy and this x. No, I haven't integrated it. I just took it out. Now I'm going to integrate it. So is everyone okay with the separation part? Now we can integrate this. After integration, this would be e to the power 2y upon 2, and this would be. And I'm going to put the plus c. Generally, we put the plus the c with the x generally, but if you want, you can put it with the y. It doesn't matter. It's just an intuitive. You just end up putting it on the right side of the x. Now, if you want to now see, your integration part is done. You have solved the differential equation. By the way, you have the general solution with you. If the question is specifically saying state the general solution, then give y in terms of x. So don't leave it like this then. Give y in terms of x. So first what I'm going to do is I'm going to multiply by 2 on both sides to get rid of the 2's. So multiplying by 2 on both sides means I end up with this. This becomes 2 times c. Now is 2 times c another constant? So let me just name that constant a. Let's say 2 times c becomes a, another constant. I don't have to write it as 2c. It's redundant to write it as 2c. We can just write the 2c as another constant a.
Can't you just write C?
Generally, the idea is to write with one constant. Otherwise, it's just too many numbers together and there's no point. So it becomes a constant a. Now I'll take ln on both sides to get the y down so that I can make y the subject. So are we okay with taking ln on both sides? We take logs ln on both sides. So I just write here I will take ln on both sides. And this 2y will come down and ln of e is a 1, so I don't need to mention that. And this becomes just ln of x squared plus a. And then I can say y equals half ln of x squared plus a. This is my general solution. General solution. And we all know why this is the general solution, because I still don't know the value of A. Once I know the value of A, then it will become a particular solution. Are we okay with this?
So when you plug in the values, you give me the particular solution.
That's why the values are given, so that we can get the particular
So
solution.
A बता देंगे, फिर वो particular नहीं होगा.
No, if you don't know the A, then it's a general solution.
We will put in my x and y.
We will put the x and y, find the value, and then it will become a particular solution. So the x and y that is given to you, if you go back and check, is x0, y0. So for x equals to 0, y equals to 0. By the way, this is an initial condition. This is an initial condition. This is not called a boundary condition, it's because x is 0. So for any x0 set of values, it's called an initial condition, otherwise it's called a boundary condition. Okay, so we got an initial condition, we plug in the initial condition, and y0, x is also 0, so we end up with half ln A, right? Which means ln A is equal to 0, which means A equals 1. Right? Okay, now let me just tell you something. When you plug in the initial condition to get the value of A, you don't have to necessarily plug it here. You can even plug it here. Plug it here. This is where we have it. You can plug it here without the error. E of 2y is equal to x squared plus a. You could have just plugged it here, you would have gotten the answer. You would have gotten the answer here as 1.
But we have to show the general form.
Because the question is because the question is asked for it. And why I'm saying this, because a lot of questions will not ask you for the general solution, they will directly ask you for the particular solution. So then this form is not required. From that point, you can plug in the values, get the value of A over there only. And from that point, you can just give the particular solution as y, make y something. You don't have to get to this point. Only you get to this point, only if the question explicitly says get the general solution. Right? So now you have a choice. You could have plugged in the values either here, or you could have plugged in the values there in e2y x squared plus a without the error. And you would have gotten the same value for a as well. You would have gotten the same value. Sometimes people will find it easier to plug it there and get the value, sometimes they will find it easier. Sometimes you find it easy to plug it, so it's your call. Okay, so we got the value A is 1, therefore our solution is y is equal to half ln x squared plus 1. This is our particular solution.
We can write the half as a square root, right? If you
Yeah, you can write half as well. Are we all good?